SHREC 2021 Quantifying Shape Complexity is a joint work of M. Ferhat Arslan, Alexandros Haridis, Paul Elvorsin, Sibel Tarı, Charlotte Bressy, James D. Gardiner, Aslı Gençtav, and Murat Gençtav. And here is an overview of this talk, and let's start with the talk itself. So shape complexity is studied across several fields such as psychology, design, and computer vision. And it has the potential to be useful in shape retrieval, measuring neurological development and disorders, or determining the processes and costs involved for manufacturing products. Our main motivation for this work is that there is a lack of comparability between methods. So, first of all, there is no benchmark dataset in the literature. As a result of this, each shape complexity paper comes equipped with their own dataset, which renders the task of comparing the methods pretty hard. And secondly, there is a lack of comparison scheme, in the sense that there is no canonical way of evaluating the performance of a method, of two methods, even if they agree on the same dataset. So our contributions are as follows in this work. Firstly, we have created two novel shape collections with associated ground truth, and we have repurposed a previous segmentation benchmark for assessing complexity measures. Secondly, we have evaluated the performance of a selection of both 2D and 3D classical and recent shape complexity measures. And thirdly, we have assessed the similarities and differences between different measures by using pairwise correlations and by clustering based on their performance with respect to multiple ground truths. So, the shape complexity has an ill-defined nature, and because of this, our dataset contains three shape collections with different characteristics. And our collections are as follows. We have perturbed basic shapes, parametric shape families, and manually segmented shapes. On top of this, we have also created 2D analogs of the shapes to include 2D complexity measures into our study, because the vast majority of shape complexity literature relies on the 2D representation of shapes, or rather works on the 2D represented shapes. And our first collection here, our aim is to explore the correlation between shape complexity and magnitude of perturbations of basic shapes. And we use a cube and a sphere as the basic shapes here, and we make a distinction between additive and subtractive perturbations. The perturbations are introduced stochastically, and we have two parameters here, the width and total count parameters. The first determines the area of effect of the perturbation, and the second determines how many times a local perturbation is introduced to the shape. For each basic shape and perturbation type, there is a separate family composed of 450 shapes, and the ground truth here is simple. We have this parameter C and W, and they constitute the ground truth by themselves. And our second collection is the parametric shape families. And here, the shapes are inspired from 3D models and designs found in the fields of architecture and urban design. The collection is composed of two families. First one is that of stacked cuboids differing in number of cuboids and side lengths with an additional rotation factor. In the second family, the number of cuboids are restricted to be either 3, 4, or 5, and they differ in spatial arrangement and in the heights of the cuboids. And there are 25 shapes in each family, and here the ground truth is less trivial. We have two experts to provide us with the ground truth, and they have compared the shapes qualitatively and aiming to determine the difficulty of modeling a shape in a 3D space. And as a result, they have divided the shapes into groups such that the shapes from different groups are considered incommensurate. And our final collection is that of manually segmented shapes. And here our aim is to explore how shape complexity measures correlate with the number of segments of different segmentations of the shapes. And we have used the Princeton segmentation benchmark. Both the dataset and the segmentation information are from there. And we have considered the human-generated segmentations to be the indicators of the complexities of the shapes. And here we have two ground truths. First is the order induced on the shapes by the mean number of segmentations, meaning that the more parts that a shape has, the more segments that a shape has, the more complexities. And in the second part, in the second ground truth, we consider the order induced on the shapes by the standard deviation of the number of segments, meaning that the less in agreement the human subjects are on the number of segments of a shape, the more complexities. So how do we evaluate the performance of the methods? Well, because the reported numerical scores of each method differ in range and numerical sensitivity, we have evaluated the methods based on the increasing complexity order they induce on the shapes. So we compute the Kendall's rank correlation coefficient between the order induced by a method and the order indicated by the ground truths. The only exception here is the second family of collection 2, because their shapes are grouped such that shapes of similar complexity are in the same group, and ideally the shapes in the same group would have the same complexity scores. So instead of using Kendall style, we are using non-uniformity score basically to evaluate the performance of the methods there. And before presenting the results, let me introduce our participants. So we have considered in the scope of this work 19 methods, and here you see 16 of them are listed, and that's because some methods provide two different scores, which is perfectly fine by our SHREC guidelines. So this includes Gardiner et al.'s work and Rosin's work, and additionally we have Matsumoto et al.'s work, where we have also considered a variant of their measurement that uses standard deviation. And the oldest work we have considered is from 1989, and the newest one is from 2020. And of the 19 methods, 4 of them are 3D and 15 of them work in 2D. So let us proceed with results. So these are the tables for collection 1, and here basically we report the average Kendall tau scores for the families in the collection 1. And on the left hand side we see the additive perturbations, and on the right hand side we see subtractive perturbations. For subtractive perturbations we consider only 4 methods, because in the case of subtractive perturbations the projections may mislead us, because they appear only when they appear on the border of the shape, which interferes with our controlling parameters. So we have discarded that case. And in the tables here and in the following tables, the higher scores are usually better, but in general we have marked the best performers via red, followed up by green and blue for the second and third best performers. And the results are discussed much more detailed in the paper, but our main takeaways from this collection is that none of the methods outperforms the others in all cases, and that the noise is a non-trivial factor for the quantification of shape complexity. And if we are to make any suggestions, we might suggest for additive perturbations Arslan and Tari's method and Gardiner et al.'s method, and for overall robustness Genchtau et al.'s method can be preferred. So results and discussion for collection 2, we have a similar table here, but here the second scores are of non-uniformity measurements, and the lower it is the better. The coloring indicates that as well. And again, our main takeaway from here is that the classical measures supported by psychology experiments are better alternatives for quantifying perceptual complexity. And Wang et al.'s, Salim et al.'s, Wassel and Giraudon's, and Page et al.'s methods are the best performing methods here. which are all 2D. And results and discussion for collection 3. Here again we have a similar table acquired by Kendall-Tau scores, average Kendall-Tau scores, and mu stands for the mean considerations and sigma stands for the standard deviation considerations. Remember, we had 2 ground truths here, and as you can see, scores are pretty low when category-wise scores are considered, and when we consider all of the shapes we get higher scores, but still it is nowhere close to the other scores that we have obtained so far. And we can say that performances of the methods improve significantly when the entire collection is considered, as I said. And from this we can say that the task of correlating complexity with the segmentation is harder when the shapes are from the same category, which might be expected. And we see that all of the top performers are 2D methods except for tau mu category, and this might mean that loss of information via projections might be favorable in some cases. Now, using these results, we present clustering of the methods in this tau-based feature space, and we use stochastic neighborhood embedding for that. We use 2D embedding, and on the left-hand side you see 17 measures that is used, and it does not include collection trees results. And on the right-hand side we have collection trees results included as well. And clearly some clusters occur, and happily the acquired clusters are in accordance with our expectations from the methods. Now, furthermore, we have used cross-method correlations rather than just using correlations with the ground truths. So when we consider this, of these 8 categories, we can clearly see from these heat maps that each category accounts for something else, reveals something else about the methods, and the correlation among the orders induced by the measures convey insight into the ill-defined concept of shape complexity, in the sense that 2 measures may, for example here, may correlate well with each other, but not so well on another family of shapes, for example. Furthermore, we have that different collections provide different means for distinguishing between methods. For example, collection 2 distinguishes Page et al.'s work from Vassell and Girodon's and CCRE, which is that of Fangs, and these are otherwise always highly correlated. And similarly, collection 1 showcases the difference between Matsumoto et al. And its variant C sigma that is not captured by other collections. And we observe similar clusters to those acquired by stochastic neighborhood embedding. And we proceed with concluding remarks and future directions. Here we have proposed a benchmark dataset and an evaluation methodology for the quantification of shape complexity. And the proposed methodology is a significant improvement on the current literature, as the reported scores are quantitative with justified ground truths and the analysis is reproducible. The methods are evaluated not only with respect to the ground truth, but also with respect to each other under a variety of ordering tasks. And the correlations between the segmentation as a proxy task and shape complexity can be explored further in a future work. And as a concluding remark, research in 3D shape complexity is still in its infancy, and further investigation of the correlates of shape complexity are needed. And here is the list of our references used here. And I thank everyone for listening, and I would be more than happy to answer any questions that you might have.